we'll get this party started. You don't want to be recorded, don't speak up. And I have to hit the share button, which is right in the way. All right, let's take a look at this. All right, we're going to go over structured concurrency today. First question I have for you guys: when you hear concurrency, what does that mean to you? What's your understanding of the word concurrency in software engineering? Anyone?
Like organizing and managing structure into predictability?
That's the structured part. What about concurrency?
Concurrency, I just think of like multiple clients, I think, interacting with the server, right?
Okay, that's good, LaShawn. That's on the right track. Anyone else? Concurrency. I'm trying to gauge how much you guys know, so how in depth we have to go. So new concept for a lot of people. Concurrency means to run things in parallel or at the same time. So like LaShawn said, concurrency, multiple clients to a server. Structured is that, hey, I'm going to structure it. Specifically, we're going to talk about structured programming a little bit. We're going to see the differences between structured concurrency and non-structured concurrency and structured programming, which all of you guys already know how to do. You may not know that it's called structured programming, but that's what it's called. So we'll talk a little bit about that. Let's first start off with what we're going to talk. Well, we're going to talk about what is Java's structured concurrency model. We're going to talk about embarrassingly parallel tasks. When I say embarrassingly parallel, we're talking tens of millions of parallel tasks running at the same time. This is something Java can handle. And then because it leverages virtual threads. So we'll see how that all works together. Okay. So concurrency. Concurrency is the ability to run multiple tasks at the same time to get something done, right? This is used a lot in like high performance computing. What they typically do is you take a big problem, let's say some kind of simulation, and I want to run that across several machines. Several machines meaning 10,000 machines. I'm going to run the same task over that many machines and over probably times that by 100 different threads. That's a very common use case for high performance computing, simulation of all different things, whether it's weather, nuclear explosions, genomic research, all those things. I take a data set, I break it into small chunks and run the same sorts of things on that. One of the biggest problems that we have with concurrency is the management of the tasks when they finish and when the next task can occur. Because most of the time when you have a massively parallel system, you need the task to finish before you can move on to the next step. But sometimes what happens is you get these orphan tasks that sit out there and they start building up over time. So a lot of times, especially like in high performance computing, what they will do is something really crazy. They'll clean the systems by like rebooting them or wiping them out and restructuring them for a new run. And you get rid of all these orphan threads, all these orphan tasks that have been accumulated over running these things over and over again. And there's been a lot of really incredible orchestrators that have been built to handle and manage these massively parallel programs. But they're very complex. And not a lot of languages support it natively. Now, so in Java 19, they came up with the idea of structured concurrency. And you guys know what structured programming is. You're used to it, right? It's simple concepts of I do step task 1, then I do task 2, then I do task 3. If I run task 1 and 2 in parallel, I wait till both of them finish before I do task 3. These concepts are important, but the languages weren't supporting them natively. Now with Java 19, they do have the concept of structuring them. So I can say, I want to run all these things in parallel, but wait until they all finish before I move on to the next thing I need to do. Some of the new modern languages like Node.js has structured concurrency built in, even though it's single threaded, which is really kind of interesting. It has the concepts of that we're going to talk about today. Go, Rust, and some of the other ones have these same concepts. So the concepts are transferable across multiple languages. So it's important to understand these concepts. Okay. All right. So let's talk about structured programming. First off, big question for everyone, and I think you could do it by a raise of hands. I think we can raise hands in Zoom. How many of you have programmed in assembly language or BASIC? Not Visual Basic, plain old BASIC. LaShawn has. Reed, thank you, Reed. Anyone else? All right, we're getting more people. Those languages are not structured languages. They use for loop, they use go-to statements. They don't have the concept of for loops. They don't have if statements. They have compares. They don't have while loops. These are structured concepts that are introduced in higher level languages, right? So most of us already know how to program. It's structured. And remember, the machines don't care. The concept here is that it's easier for us in the way that we think. Most humans think in a very stepwise structure. If this happens, then do this. While this is still working, run through this. Or the concept of calling out to a function. I'm going to, go do this over here and then come back. Those are structured concepts that are great for humans to do programming in. It makes it easier for us to understand and to work at that abstraction layer, right? Well, guess what? With structured concurrency, we take some of those same concepts and now we brought them down into running massively parallel tasks that we need to get things done. Okay, so what's important here is that there's some nesting of operations so that I can mirror that structured concepts that I'm already used to. Okay, so you're going to see some of those today. So let's talk about embarrassingly parallel, and I want you guys to come up with some ideas to add to the slide. The first one here that I have is I'm going to go look for a flight that I'm flying from Sacramento, where I live, to Nashville, so I can go visit most of you guys that live in that area, right? Massively parallel, meaning I can put my query in, and I'm going to go hit a whole bunch of different websites to find the correct flight. I don't want to do those sequentially. I want to do those in parallel, right? Okay, so give me some more examples of when I would use this concurrency concept. Anyone? I'll start calling on people if you guys don't volunteer or just jump in.
To render pixels on an image, you can do that.
Yeah, absolutely. Pixar actually does this with their massively parallel when they're rendering and ray tracing their movies. They do massively parallel. Okay, great one. Anyone else?
What about like data processing for like different parts of a large data set?
Perfect. Yep. They break out large data sets. Genomic research does this a lot of simulation, or think of all of the CERN stuff that they do with the super colliders, right? They've got tons of data. They break that data up, separate it out into massive concurrency, massively parallel. Anything else?
Does a neural network count?
You know what? That's a really interesting one. We are starting to see some neural network stuff that's starting to do massively parallel. Yep, that's a good one.
Thank you.
Anyone else? No. All right. Remember, and we've mentioned some, massively parallel can be CPU bound or even IO bound. The great news about using virtual threads on the bottom end of this is they're non-blocking to the thread above. So I can run massively parallel IO without it blocking each other. So if someone gets back early, it can get that information where it needs to. And you're going to see with structured concurrency, I can grab each information from each task as they come back, or I can wait for all of them to finish before I get the information. Okay. All right, let's take a look at the concept here. And let me move I've got my thing in here. All right, so they introduced this concept called structured task scope, right? So the structured task scope is kind of a way of me saying, hey, I'm now going to run a bunch of tasks, and you now have established a scope, okay? Then I can go through, and you're going to see some new terms in here like future. We'll talk a little bit about that. But the other things that you're going to see is I also use the concept of fork, which would be something you guys are used to. And I also have join, right? So I've got a fork out there. I've got join. I've created a scope that is controlling all these things, and I can go through and list it. So let's walk through each one of these first. So the first one is I'm defining a scope for splitting a task into concurrent subtasks. So I'm saying this function that I'm writing right here, I'm going to create a scope that I'm going to create subtasks underneath. So that's the first thing that I have on here. If you notice, it says shut down on failure, right? That means if I do throw an exception, that I can stop the higher level scope will be over. Okay. In this case here, I'm also saying if I get a failure or when everything finishes, then this task will be done. So that's what I've stated with that right there. Okay. The next thing here is I'm using that scope to fork off new threads that are going to be handling the work that I need to do. So these threads are virtual threads. What's the benefit of virtual threads? We talked about it last week. Do you guys remember the benefits of virtual threads? Anyone?
And there's small units of processing.
Yeah, they're really small. They don't hog up a lot of resources, and they spin up really quick, and they're not dependent on the OS kernel for resource allocation. So it's all handled in the JVM itself. So this is good news, right? Because it can be quick. What's the other benefit of virtual threads as far as scalability? How many can I have? How many virtual threads can I have?
It's multi-threaded, right? Like that, isn't that the multi-thread? You can have many.
I can have 1,000, 10,000, 1,000,000. These threads are so small, I can launch them, and they only load memory dynamically as they need it. So they're very, very fast, very small, and I can run millions of them concurrently. Where with a normal thread, it's far fewer, right? We're only talking thousands. And there's at least a 1 megabyte overhead for each real thread that's out there. Okay, so this is taking advantage of these virtual threads. This is important to understand. Okay, it probably will be on the exam on February 6th, if I remember the date right. Okay. So here I'm saying I'm going to fork, and I'm going to go do this work which is reduce and multiply a big fraction, and that's work I'm going to do. Okay. All right, now let's look at the next. All right, here I'm adding a future of each computation into the result. Now, this is something really important. We'll talk about futures, but think of futures as this. A future says, in the future, I'm going to get this result out. And when I do get that, add the future now, and then it'll populate when it is resolved. So think of future. In other languages, they use the concept of promise. If you've ever heard of promise, promise and future are the same concept here. Okay, so here with result.add, I am adding a future to from each result into the results array of futures that I have there. And then here, the line here, I'm saying with the scope, I'm going to join all the threads that I forked, and I want them all to finish. Or if one of them shuts down unexpectedly or throws an exception, then I'm going to fail. Then I'm gonna quit. And then that will end that scope, which means now I'm not blocked anymore. Now I can carry on the control that the flow of control that I had scheduled before. Okay, so any questions? Oh wait, here's the last one. I'm going to process the results, which are all now stored in those future objects. And I'll only do that once the join is finished, once everything comes in. So that's that sort and print list of the results. This is really important that the results will actually have all the real results once all the forks are done. Okay. Anyone have any questions on the syntax, on the structured concurrency?
I have two questions. My first question is there not a garbage collection we have to call on the thread to clean it up when it?
No, you don't. That's a great question. That it's all handled in the structured task scope. It's all handled in there for you.
And my second question is, there are two exception handlings done here. Does that mean we don't have to put a catch on the try?
No,
Or
there
like-
would be a catch. There would be a
Okay.
catch on the try. Yep.
Thank you.
Yep. Good question. Any other questions? So before, if you were writing this pre-Java 19, you're right. You would have to manage all your threads and do garbage collection on all those threads, make sure nothing was left out there. And inevitably, people don't do that. And we end up with a whole bunch of threads, and people are wondering why their machine is so slow when nothing's really running on there, but they actually are. You've got a bunch of threads that are still running in the JVM or even in the OS kernel. So the idea here is that this manages the threads for you more effectively. Okay, so we talked about the scope join here as I only am done, and I only do the sort and print list when all the threads are done, or if I get an exception here. Okay. Okay, so here's another way of looking at it when we're looking at a program flow of control. This is using UML, which I'm a big, huge fan of demonstrating the same concept here, right? I've got perform task A. When perform task A is done, then I want to run these 4 tasks in parallel. And when they are done, then I'm going to run the task complete on the end of it. Okay. The flow of control is important here, and structured concurrency basically allows me to create this scope, which is this horizontal bar here. It basically says, hey, I'm going to create this scope, and everything in between the horizontal bars is in my scope. And when I say join, that's down here at the bottom. I'm going to join all of those tasks together before I move on. So this is a way of denoting that same concept. Okay. All of the threads begin at the scope. Now, this is important to understand. When you're dealing with concurrent programming, you are not guaranteed the order that these threads will fire up. Now, there may be an order and it may be somewhat consistent, but you're not guaranteed that order. And you're not guaranteed the order that they're going to end. So if that's the case, what are some things you need to watch out for? What about these tasks that you need to watch out for if you're not guaranteed order of execution?
I've done many of this in the front end with race conditions. That's the big one. Things showing up before you're expecting them to.
Good, Jonathan. Yeah, race conditions or things showing up before, like maybe task B sets a little flag or register that task C is looking for. That's bad mojo, right? You don't want these tasks to be dependent on each other in any way, shape, or form if you're running them in parallel, right? Because you're not guaranteed the order of operation. Okay. Anything else about task B, C, D, and E and what's the right word? Non-reliable order of execution. What's some other gotchas that you need to watch out for?
Does that make your results inconsistent?
They could make your results inconsistent. Yeah. Especially if you want them to come back in a specific order. A great example of that, let's say I want to alphabetize a really large list. I want to alphabetize a really large list. And I decide I'm going to do this massively parallel. I'm going to create 4 threads or 400 threads. And I want it to alphabetize things. Is this a good design pattern?
It might alphabetize each thread, but once you're trying to join them, it may still leave you in the same mess.
Yeah, you still may get in the same mess, right? Right, exactly. So there's some other tricks you can play to massively, like saying, hey, everything that starts with the letter A goes to task A, everything with B all the way up through Z, or there's some things you can do there. But remember, the idea is that they're independent. The only time that they come back together is at the join, right? And that's when you can bring the information back together. There's no guarantee of order of operation. So you got to watch out for that, okay? Also, subtasks do work on behalf of the task above it. The task waits, and the term that you see in other languages, they use this concept of async await, and this is the same concept. The task that has the subtask underneath it, it waits or awaits the subtask results and then monitors them for failure. So this is really cool in structured programming. If they fail, I can say if one of them fails, then I'm going to shut down everything else, because if one fails, then they all will fail. Is that always going to be the case? Do you always want to do that? Probably not. So they have different models. They have different operations. Like, I want to run everything to completion. Even if one fails, don't quit until everything's done. That may be an option for you. Or another option, I may want to run everything in parallel, and the first one that finishes wins, and I'm just going to take that and then kill everything else. That could be another option. Okay. And I'll show you how they have some syntactic sugar on how to do that with the language. Okay. All right. All these threads, like we talked about, and in this diagram here, all the threads must complete by the end of the enclosing scope. This is still true. Excuse me. Even if I have one that errors out, I still will not leave a thread behind. Meaning, I'm going to kill those threads. I'm going to kill those tasks, even if they're not done, if that's what I told it to do. But I am not done until everything is cleaned up. And then I can move on, right? This prevents threads from being leaked and things like that. So that's, what's happening underneath the covers may be, they may be doing some garbage collection for me, but conceptually perform task A, all the tasks inside of it have to be completed, whether they were forced to complete or whether they were, whatever, or they aired out or they finished before I move on. Okay. All right. This leads to no orphan threads like we talked before. Yeah, here's another really cool theme that is really interesting. I can actually have nested subtasks, and you can go infinitely deep on this. I don't know why you would. Most of the times, if you're doing 2 levels deep, that's probably sufficient. Maybe 3 levels, but what this means is I can have task A that has subtasks B, C, D, and E, and each one of those has 3 or 4 or 500 or 5,000 subtasks in it. And the same concept, this structured part says that task B won't finish until all of its subtasks are in a completed state. And same for each one of these. And then also task A is not, in a completed state until everything every one of its subtasks are complete as well. Okay. Does this make sense? Everyone understand this concept? Is there anyone that does not understand the concept? They need to go over it a little bit more. Don't be shy. Now's the time to learn it.
How is debugging with this?
Debugging with this is really interesting. So especially IntelliJ actually does a pretty good job at you being able to put in breakpoints in your subtask. Now, which subtask you're in can be found in the context of the thread itself. So if I'm stopped, let me show you. Let's say I put a breakpoint right here in reduce and multiply, and I put a breakpoint right there because I want to debug this. When I come through, I'll be able to see in my local variables what thread I'm in. I'll be able to see big fraction and S big reduced fraction. I'll be able to see all those things. If you put a stop in here and you have 10 million, it will break on each thread as it gets into there. So
Okay, so you'll see
Yeah.
it like stopping. How would you start from each thread? Like, do you get like breakpoints spread out wide, and then it's like, oh, I got to start this one and this one and this one and this one?
you don't have to start them. They'll stop. They'll come through and they'll stop, and then it'll show you the latest one or the first one that got there, and then you'll say,
Okay.
all right, start that, and then boom, it'll hit again.
Okay.
So if you are debugging, my suggestion is don't put your count up really high, right?
Right.
Don't do 10 million and put a breakpoint in there. It will be brutal, right? To get through. Put maybe 5 or 3 to see that it's doing what you expect it to do, right? That would be my suggestion.
I know from my experience debugging async stuff on the front end, try catches are your best friend, because once you can catch errors properly, and if you throw errors properly, then you're gonna find the error a lot easier than not. So
Okay, so it sounds like it's very similar to when you're doing like an async await methodology, just different words.
Different words, same concept. You know how async and await, and if you're used to, like, I'm a big Node.js programmer. I use promise all, so I'm waiting on all the promises to come back.
Sure.
Or it's the exact same concept in Java. Now the benefit is the virtual thread. So I mean, they can go massively parallel, which is really cool. But it's the same concept. Right? We already talked about this. All subtasks must complete before each parent task can complete. Remember, they can be forced to complete, or they could air out, whatever the case may be. You could say whoever's done first wins, and then wipe out the other ones. They still have to complete the being killed before I can move on. Okay. Sibling, I already mentioned this. I can have multiple sibling tasks inside the parent task. All right, let's talk about some other places I can use concurrency. Now that we've talked a little bit about this, give me some more ideas on where else I can use concurrency. Practical uses.
When you need to resolve a data source for a specific piece of metadata on the front end, maybe they exist in multiple places, but certain endpoints are faster than others, but the data may not exist in the faster endpoint, so you're running all three possible endpoints for where to get the data, where
That's
you
a-
know
that's a
you can
great one.
guarantee, yeah, you can guarantee the solved one. Yep.
I can agree with that one. I know at work sometimes they have to call like 3 different external providers of data, or 3 plus, and they need to get all this data, which may come back in a sync manner. So can definitely see where that would benefit.
Great. Any more from anyone else?
Yeah, what about with like AI or like machine learning, like to speed up like your model training and interface by running the tasks in parallel?
They absolutely do that. Yep.
Speaking of AI, I know if like the new NVIDIA chips, I heard that they were using concurrency more in the actual calculations for that. Would that be a way they would do it?
You know, they could do it that way. There are some constructs even lower down underneath Java where if you're using the right math libraries, it's handling a lot of the concurrency for you automatically, and taking advantage some of some of the accelerators that are built into GPUs or even on CPUs now. And you guys know I work for Intel, so Intel has quite a bit of acceleration in the CPUs for massively parallel math operations, for matrix math operations and things like that, where I'm doing the same thing, you know, 10,000 times on a 10,000 by 10,000 matrix or a million by million matrix. That's massively concurrent type stuff. But that stuff's way underneath the covers, but underneath the covers of these languages. So they'll handle a lot of that stuff for you, which is
Use concurrency on logs, like logging.
ooh, yeah, that's an interesting one. Processing logs concurrently, or are you asking the question, how does it do logging?
Well, I was talking about rating logging output where you just fire it off and then you're doing your other stuff while you're waiting to write logs, just as like another part of IO processing, right?
I like that one, Aaron, especially if you're blocked on slow IO, if anyone's still using spinning Rust, as I like to call hard drives. They're very slow compared to the CPUs and memory and solid state drives. So yeah, that would be a good reason to, hey, I'm just going to run that off there and let it go and do its thing.
What about with like cloud computing for like balancing workloads and such?
So are you talking about the orchestrator itself? Well,
More like would you be using concurrency to like maximize like that, like distributing workloads? Like is
yeah,
that
yeah, that's a form of concurrency. Yeah, absolutely. Okay, let's move on. Let's do an IO example now. Okay, because we've shown a CPU example. And the more examples you see, we're going to see different things, okay? So first thing is what? Define my scope, right? And I define my scope as structured tasks, right? Structured task scope. And I'm going to shut down on failure, right? So if I do get a failure, I'm going to shut down, all right? Or I'm going to wait for all to complete. Okay. All right. Next thing I do is I look at, hey, if I want to spin up a virtual thread, I use the fork concept from the scope. And then I have it download images here. So now I'm going to download images. I have a list of URLs that I'm just going to download images from web pages. That's all this is going to do. Are they all going to come back at the same time? No way. No way, no how. Some websites are slower than others. It's all over the place, right? So, but you can see that I can do this for IO bound as well. All of them will try and do it in parallel. They're not going to wait on each other because we're using virtual threads that are non-blocking to the higher thread that this is all running in. Okay. This block of code is doing what?
Waiting for them all.
Waiting for them all to come home, right? When they're all done, then I'm going to return all the images at once. Okay. Now, if I change this, then I'm going to change this to exit if there's an error with any of the downloads. See if the throw if failed. So if I don't put the throw if failed in there, then I wait for them all to finish. Even if one of them fails, I need that throw if failed in order to now tell the shutdown on failure, to tell that scope that, hey, if one fails, then shut everything down. If I don't put it in there, then it will wait. Even for failed ones, it will wait until everyone comes back and then return. Okay, this is important. Don't
Are we going to Are we
Yeah.
going to talk about strategies for, like, let's say you've got 3 different threads and they're all doing some type of data mutation, and 2 of them work, but one of them fails. And you probably have something that you're expecting to be like atomic at the scope level, but somewhere in the middle, 2 things worked, one thing
Something
didn't.
doesn't. Yeah.
Yeah.
Yeah. Let's see if we have time to talk about it, because those strategies, those are, you could go through several different ways of doing that, Aaron. Checking the results back. You can let's see if we can get to that at the end. Okay, Aaron?
Yep, sounds good.
No, that's good. And if we don't, then that'll be a great for discussion on assignment 1 in the discussion thread. Okay. Let's talk about some of the benefits that we get here. Some of the benefits of structured concurrency, as you know, and here's another example here, right? I've got another example. What's going to happen in this example? I'm going to wait for the 2 find user and find order. I'm going to wait for them to finish unless one of them fails. This is another way of saying, you know, throw if failed. I don't have to tie them in directly. This is just syntactic sugar here. Okay. So greater clarity. Look, I create the parent-child relationship with the fork here, right? So these 2, find user and fetch order, are children of the scope of the try, right? That scope that I have there. Okay. So this gives me that ability to create that child parent relationship between tasks. Short circuit handling. If there's any issues inside here, I can throw my exceptions directly out of there. And then with this, I can short circuit the other one from moving forward, which is the concept here of the interrupts. I can support interrupts. Okay. This is much easier to read. In fact, it looks somewhat, I didn't say completely, because we're going to talk about some of the cons on this as well. it looks somewhat like a normal structured program that I have where I'm finding the user, then I'm fetching the order, and then I'm returning the response of both in a return. It kind of looks like that as I've got find user, I've got find order, and then I've also am returning the results. You can see there's more involved there, but it's easier to read than what I was doing before, which had coordination scripts and all that stuff. We talked about the invoke all or invoke any, which is that concept of the join. The join says do everything, or if there's the invoke all right there, I'm going to do everything until one fails. And this one's interesting here. This is the invoke any. So this is where I'm saying where I get a result back, it's going to block until the first successful result is available, and then I'm going to go for it. I'm going to head back. Okay. So if I do the result invoke any in this one, it's kind of a dumb example. I hate to say that, but it is, because my response is only going to get one of those, a user or an order. The other one is going to be missed. And do I know which one it is? I have no clue.
So wait a sec, I thought the scope.join waited for everything.
But the result here makes it so I'm waiting for just one result. And once I get it, then I'm good to go.
Oh. Yuck.
Yeah. So join says yes. Result says I'm just going to grab one result out of my subtasks. And I don't know the syntax, Aaron, for saying, let's say I had 4 or 5 tasks. If I said, well, if tasks 1 and 3 finish, I'm good. Let's move forward. If 2 and 4 and 1 finish, then go forward. I don't know how to do permutations of results, but I'm assuming they have that capability. I'll have to research that more. And that'll go into some of your strategy type concepts.
I suppose you could use multiple scopes, and that would probably be
That, yeah, that could be really hard to read, though. I don't know. Well,
that's an
can research
assessment I
that.
have of Java in general.
Yes, I know.
So
It's not my favorite language.
So the one thing I'm just trying to get in my mind for this is what case would you need it to be where you would only need like one result? So the only thing I can sort of think of for that would be like randomizer mechanics. Sometimes they, like, if you were to look at some probability mechanics for how people calculate whether you're going to get something in a game or something.
Oh, you know, there's
That's one way I could see it used.
yeah, there's another one, and that is sort. Let's say I've got a really long list of things I want sorted, and I've got 4 or 5 different algorithms. And I don't know up front, because it's unordered, I don't know up front which one would be best. And if I want to write a generic thing, I can say, you know what, I'm going to run sort across these 5 or 6 different algorithms, and whatever one comes back first, that's the one I'll use, and I'll kill the other ones.
Yeah, makes sense.
Yeah. And in fact, I will post up tonight after class. I'll post up some videos that Dr. Schmidt did, Doug Schmidt, on he gives even more examples of concurrent programming, and he gives several different examples, full-blown examples on the code and the different use cases for doing it.
Yeah, one use case I definitely thought of during this was procedural generation could definitely be used for this. Like if you think of everything as like 4x4 puzzles and like a 4x4 puzzle, and you're just trying to fill in the piece, you can do that almost infinitely.
Yeah, that would be good. Or another interesting one where I just want one result is I'm I'm asking several public Gen AIs to do something for me. And I want whoever comes back first. That's who wins.
Or if you're mining Bitcoin, you know, you send
That's
out
right.
you send out the like go find the hash, right, to like 500 different banks of servers, and you only care about that one number. It's going to take a lot of processing power to get it, but once you've got it, you only care about one of them.
Yep. Here's another good one.
I have a quick question. It says the result will return the first successful result is it if it's available. How does that work with throw if fail? Because if the first one happened to fail, wouldn't it just stop the program anyway?
It would. So remember, there's no order.
Yeah.
So if one of them fails, boom. If that failure happens before one of them results, then I fail. If the result happens, then it's going to go kill the other ones. It's like, I'm done. I found a result. Everyone else, I don't care. So, you're done. And then move on.
And just for my understanding, so when you run these, you can also, instead of having it throw, you can let it still run and just can you avoid throwing if you wanted to for this? So say find user fails, but you don't want it to actually throw.
Yes, you absolutely can.
Okay.
Yep. It fails. It won't give you back a valid thing, but order will continue to run. If find user fails and fetch order hasn't been completed yet, fetch order is going to continue to get to try and do its stuff. Yep. Okay. Well, here's that example. All right. Here's some of the cons of structured concurrency. And you already brought up some of it. One of them is this concept of future. It's awkward and limiting, right? Because if you see here, I've got like, I'm going to sort a bunch of lists right here. You can see that I don't pass back the sorted list. I have to pass back a list of future of those things, right? So syntactically, it's a little bit more to work with, right? I have to make sure that I'm turning my futures here into a list of objects as well, right? When they come back. So this is the awkward part of it, and it can limit me in some things. Like I can't chain things together like I could in outside of this scope. I can absolutely chain different functions together. I can't really do that because of futures, right? It's also, as Aaron mentioned, quite verbose. That is a lot to say, hey, I want to go sort a bunch of big fractions in parallel. That's a lot to say that right there. Right. So there are some downsides, but it's far better than it was, is the key. Okay. All right. Any part of this that you guys want us to go over some more before we start looking at assignment 1B? Anything we want to cover in more depth? Okay, I'll take the silence as not right now, Dr. Darren, because we're tired of hearing you talk. Okay. Let me hit the stop on the record.